So as I promised before, now I will be explaining this bottom-up approach for constituency parsing. And like the previous lecture, part 2, I'm using pointer networks again. So, but this time from Shanghai University. Last time was about Singapore, I guess, but this time is about Shanghai. So I've implemented this in PyTorch in a different way, because you can implement this in different ways. So sadly again, you assume that you have your labeled data, you have those tree banks, and with perfect labels and parsing, and you know everything. So you don't need part of speech. But if you use unsupervised learning, knowing part of speech is enough. You can generate all of those things. But in this lecture, we are not talking about unsupervised learning. It is supervised, and we are using it for constituency parsing. And also it is bottom up, because it is less risky, as I said. If you go from bottom to top, if you go from here, find these and then finding other constituents here and to the root. So this way is less risky, because you know that you have got the basic terminals, and it has a pre-processing, which is which may be not good, because you need to do lots of pre-processing to prepare your data. But anyway, the idea is beautiful. You're using the pointer networks. So there are many interesting things in supervised learning that any deep learning engineer should know. One of them is the pointer network, pointer net. The other idea is CopyNet. CopyNet is very important, because sometimes you don't have your vocabulary is not enough. You have some words in the input sequence that you cannot even find it in the vocabulary. So you should copy that. So it's a trade-off between copy and pointing. So it is CopyNet approach. There are other paradigms for supervised learning. But on the other hand, you have unsupervised learning approaches where you use expectation maximization, Viterbi, in or outside algorithm, and those things that you need for if you want to do unsupervised approach to dependency parsing. And it was all started in 2004 by the work of Christopher Manning. Very beautiful work, which was so inspiring that many papers were generated after that, especially the guys in Alibaba in China in 2021. I think they created a very interesting paper that it is evolution of the work of Christopher Manning, which was initiated in 2004. Of course, we cannot say that this unsupervised learning is initiated in 2004. It goes back to 1977 or 1987. So this is unsupervised learning is essential when we don't have expensive labeled data and crowdsourcing is expensive, or you're using it with not popular languages. So the only data set that we have lots of the supervised learning training data is English, but it is good to use unsupervised learning for other important languages such as Persian, Greek, Hebrew, German, French, and so on. So this approach is, as I said, supervised learning. This approach that I'm talking today is bottom-up approach. You go from the terminals, you find the terminals, and you go to pre-terminals. We call them pre-terminals, and then non-terminals, and finally you go to the root, which is the sentence. So you should memorize all of them. I mean, the neural network should memorize all of these. And we use the pointer network as usual. So you see that, for example, at the next time step, it should point at which boundary, and we are just learning this. For example, when we are at 0 and 1, which with the label MP, the next one is pointing at here, the red one. It is 2. But the cursor is at here. But at the next step, the cursor remains at the place that your pointer was. And it repeats. For example, here you understand that this is the pointer, but you put the cursor at the previous pointer, and so on. You find the next pointer, and then you put the cursor at the previous pointer, and so on. So you go up. So this is good if you don't have a kind of skip. And in this, because we are doing constituency parsing, this skip mechanism that I created is not useful here, because the problem is very simple. So here we have so we have two things: cursor and pointer. So we are learning these things. And we know the oracle, and we assume that we know all of those things because we are just learning in a supervised fashion. And here is the idea. So we have a decoder. As I said, decoder is most of the time LSTM, but the encoder is bi-LSTM, because we need forward and backward in bi-LSTM to know when we move from different direction, from left to right, right to left. And here we use BERT. You could use, for example, glove embedding and download that 1 gigabyte file. So there are different ways to represent it. And after you give it to the encoder, it uses the same kind of trick. And this is the idea that is inspired by Christopher Manning in 2017. This article from Shanghai University is inspired by that idea again. And so we have our boundary and span representation. Here we use the same trick that I explained in the previous lecture. So you see, all of these ideas are copying themselves because they are beautiful. Why do we like to copy their ideas? Because they are beautiful, because they are so natural that we cannot find an alternative approach. That's why we copy the idea, because we love the idea. So the decoder one. The decoder is this is the idea of biafying attention that I explained in my third lecture of NLP in Python. And I've shown you the Python code, the PyTorch code, how you implement this in PyTorch. And as I said in the previous lecture, we have label as well. So you're also learning the labels. Everything is standard, nothing special. And also the training is a sum of the pointing, like the previous lecture. You add the loss for labeling. So here is like the previous lecture. And so everything is like the previous lecture, but now we are going from bottom up, bottom to top. So when we say we are at a span, for example, from 2 to 5, the next thing that is pointing is here, so 6. So 6. But so it is attending to 6, so 6 is here. And 5 was from previous span. We can just immediately find it. So 6 to 8, you go from 5 to 8, then you go from 1 to 8, then we go from 8 to 9. So we are just learning these things. And of course, they also concatenate with the label as well when they are giving it to the decoder network. So this is the decoder network, which is LSTM, and this is the encoder, which is by LSTM, and you're also feeding these, as I said, labels to the decoder input. And you're learning these outputs. So not only the span, but also the label. Not only the span, but also the label, and so on.